Sir, I think we can start, sir. Like we got 70 participants. Sir, are you there?
Fine. Yeah, I'm here.
Yeah. A warm welcome to all the participants on behalf of ECEA. We all know that electronics have made our lives smoother, but do you wish to know how it all happens? It's using ASICs, application specific integrated circuits. It's a chip built for a specific application on purpose. Today, we have Mr. Kumar Ankit, who is a senior design engineer in DFT team at STMicroelectronics. He completed his BE in Electronics and Communication Engineering from BIT Ranchi, and also he co-authored research papers as college graduate for international conferences. Is here today to provide insights about ASIC design flow and related career opportunities in electronics industry. And all the participants, please feel free to post your questions in the chat box. Now I request Mr. Kumar Ankit to start the event.
Yeah.
Sir,
Thanks.
so one thing, like, could you make a full screen, sir? The presentation so that it will be much more clear.
Yeah, fine. Is it done?
No, sir, it's still showing. It didn't become full screen yet.
Try a slideshow once. I think that.
No, I tried slideshow only. Not able to see it full screen?
No, not.
No, sir. It's still...
The slideshow button at the top beside animation.
No, actually, I have done slideshow for the PowerPoint. How is it visible to you? It's very small.
It's manageable. I think you can start it.
Okay. No. Then let me try. It's sharing a window. Okay, I think I'm sharing. I have it in slideshow, but I don't know.
It's okay, sir. You can proceed.
Okay. So, firstly, thanks Aditya for this introduction. And yeah, so I think I don't need to introduce myself now. So let's start, and let's start with not in a traditional book and copy manner. Let's start with something fun. Okay. And I want if people can just unmute themselves if they have an answer to this. Okay. So can anyone identify what is this?
Sir, I think the slide transitions are not. You can quit the slideshow and then move like before. I think that would help.
Okay. Is it not showing the next slide?
No, sir.
No.
No, sir.
Now?
Now,
Yes, sir. Now it's
visible.
Okay. So yeah, let's get involved into this. Anyone?
sir. It looked like blurred image of something spherical or disc shaped.
Okay. Okay. A more enlarged view of the same thing. Let's see. Now?
Is it a moon, sir?
No.
Moon's surface.
Yeah. No, it's not. Okay, let's go ahead. Now?
Is it some microorganism?
No, it is not.
Looks like amoeba.
Design on Taj Mahal.
Oh, who said this?
Sir, it look like a painting on the wall.
Yeah, who said design in Taj Mahal?
Sir Varun.
Okay. Varun, you're right, and I did not expect it to. See, the next image should make it clear. And now for sure, right?
Yes, sir.
So yeah, where did we begin from? That was a very small picture, a very zoomed in picture of a small section of Taj Mahal, right? Which might go unnoticed. But this activity was just to show, like, even when you people work as an engineer, you'll not be seeing the complete picture. Okay, you may be working uh, for something very delicate. You may be working on a block, you may be working on a sub block of a block, but each block and every small components are equally important. So this was just uh, I consider it fun, yeah, activity to see, like, what goes into making. So this is your final result. Okay, and each step included in that, if we compare it to how a chip is made, that we are going to discuss. Okay, so let's proceed into the technical stuff now. So these are some terminologies which you'll encounter on day-to-day basis if you go into the VLSI field or if you're studying VLSI. Okay, if you, I'll just go through each of them and I'll not go through very, like, theoretically. Let's see. So first one is wafer, because the knowledge of these are required if we need to understand what is ASIC design flow. Okay, so first is wafer. Wafer is, you would have seen wafer discs, right, in picture, or if you have not, then please you can Google and see. So it's a disk. It is actually the base upon which the circuits are made. Okay, it's a slice of semiconductor. Second is MOSFET. Um, it's like just the basic building block of all the modern day electronics. Okay, and it is the reason why we are studying VLSI the way it is. Okay, into so much of a miniature field. Uses R as a switch and as an amplifier. This is again theoretical, but you need to see. Okay, if, like, MOSFETs are used in digital and analog field both. In digital, it will be used as a switch. You either switch it on or you switch it off. It's either 1 or 0. But it has application in the analog field also. Okay, so this is the basic building block, like cells of a body. This is a basic building block of the modern day electronics. Now, to those who would have encountered MOSFET, can you tell how many terminals does a MOSFET has?
Sir,
Sir, 4 terminals.
Okay, anybody with 3? No. Yeah, it has 4 terminals, and usually people miss the substrate or the body terminal. Okay. Yeah, fine. And next point is, what is an IC? Okay, so it is upon wafer. So the first two you combine along with your circuit knowledge, and then you get an IC. What do is, on wafer you'll print the circuits. It's called printing in this term. Okay, you'll make the circuits actually, but it's not electrical, it's electronics. So you don't have wires, big wires and resistors. So we usually call it printing of a circuit. So we print a circuit on the wafer. Okay, so IC, till now it's not sure, like, till our study, wafer, MOSFET and IC, it is not about a specific task. Okay, obviously you have the NAND gate and gate IC 7400 series, IC 741. Okay, but those are not for specific task. You can use them for multiple tasks, so they can be put into IC, but general purpose IC. Fine. Now, what the industry has gone is ICs based on a specific purpose. Let's say you have a particular need that I need to measure the car speed and I then need to send it to send it to the speed monitor, and then I need to print it in a digital way. Maybe if the speed limit is crossed, I need to put a checker, and then uh, you can do multiple things. Maybe you can directly send it to a mobile directly. You can these days it is being implemented. So there's the camera on the roads, and if the speed limit of the car or bike is crossed, it captures the image, it reads it, processes it that it is greater than 60 kilometers per hour or the specified range, and then based on that your details are searched and directly you get a challan. Okay, so there here the IC which would have been used in the module, it has two functions. One, okay, to understand the data from the camera. Second, to process that data. Okay, the data from the camera is in pixels. Now you need to be that in numbers. How do you do that? Okay, so you will have to put multiple elements inside this. So this is ASIC, but now it's like more advanced, and we usually work on SOCs. Okay, it is called system on chip. It is a computer in itself. Okay, what it has is, it has everything. It has ASIC inside it. It has CPU, it has the graphical unit, memory unit, peripheral unit, all the small elements, and these are uh, the current day technology that we are working on, and SoC is the thing today. Okay, now to understand SoC and ASIC, or if they are confusing, you say this. See, this is a complete SoC. Okay, silicon on chip, system on chip. I'm sorry. So ASIC is a part of this. ASIC might be doing some functions. Let's say measuring uh, measuring body temperature. Okay, so what you would have is you need a system from outside that measures the temperature. Okay, but that will be in analog. Now you need to convert it through an analog to digital converter, ADC to digital, because ASIC won't understand analog inputs if you give it within like small time frame. Okay, it needs digital input. Then with digital input, ASIC can work, and it needs other support elements to work. Let's say memory. If you want to measure the temperature, if you have kept a device and you want to measure the outside temperature of a day within each 30-minute range. Okay, you are into maybe meteorological department, and you need that within, for every 30 minutes I'll measure the temperature. Later I'll see what is the fluctuation within a day. So you need outside this a system, a subsystem. Here it is RF or IF system. Okay, uh, radio or infra. You can have any device here that gives an analog output, and then you can process it forward. Okay, so ASIC is the main processing unit here. Fine. How is it going till now? Like, are you able to resonate? Are you able to understand?
Yes, sir.
Okay, fine. And if it goes way beyond, then I think you should let me know, because it should be like basic. I know mostly people are from, I don't know, first year to third year. So, okay, you should get an overview. So now let's go into the ASIC design flow. It is a set of steps. Okay, right from conceptualization. Like you have this thought that I want this application. I want a chip for so and so application. Okay. So from that step till the end, till the tape out, we say that is the tape out of the chip. Okay. Till the tape out of the chip, the complete flow is called ASIC design flow. Okay. So these are the steps. Yeah. These are the steps. See, this may vary from book to book and from different videos and industry, this is a generalized flow. Sometimes some steps will not be there. Sometimes some extra steps will be there. Sometimes some steps will be broken down into multiple parts. Like here, I could have clubbed some like last 2-3 steps into one, but okay. This is the most that I could break it down. So it all begins from specification. We'll talk about each from the next slide. Specification, architecture, RTL design, functional verification, synthesis, design for testability, floor planning, placement and CTS, routing, physical verification and sign off, tape out, and then you get the chip. Okay. What happens? Let me talk in brief here, and then I think in the particular slides we'll have less of an issue. So specification, as you know, you have just conceptualized that I need a chip, and the customer, let's say if it is a car company, it needs or let's say it is a mobile company, it needs a chip which senses human touch, and then it says like if you have tapped it once or twice, fine, then it is the first thing. Yeah, you need to have a need for thing. So there was a need, let's say there was a need for uh, two cameras in the behind. Earlier it was only one, now you needed two, and you needed an extra focus device. So that was the need of the mobile company. Then it comes to uh, the manufacturing company, the company that designs chip and manufactures it. Sometimes those are the same. Sometimes some companies are. So there are two types of companies: fab based and fabless. Fab is the place where chip is finally manufactured. Okay. So companies like Samsung, it has complete flow of its own. Okay, it has its own fab, it has its own design team. Okay, so it will design it from basic to the end, and it will manufacture it also in its own fab. Sometimes what happens is companies, even though they have fab, they get it manufactured from some other company. That depends on technology. Let's say they are working on an older technology or a higher gate length technology. Fine. Then they'll just design it and they'll get it manufactured from some other company. Uh, yeah. So yeah, we begin from specification, and then so like you can't have, okay, you get a need, but you can't have unrealistic ideas. Let's say like driverless car is going on, it has gone up to a good level, but you can't have unrealistic expectation. Let's say a company, it's things that um, I'll have a driverless car mm, and anything. Okay, maybe it maybe it stops it stops at signals, and maybe the technology is not such that it has been able to understand the signals colors, or it's not able to comprehend. So that thing, it will be rejected in the first step only. Okay. Or let's say it's a car company and now it wants to launch a rocket. So the chip that was made up till now was made as per the conditions of this, of like our environment. Now it has expectations like like you manufacture a chip which will not require any outside intervention, and it will help me launch the rocket in space. Fine. So there, these are unrealistic ideas, and it might be rejected in the specification stage, and here the negotiations go on. What happen is the company which will ultimately design and manufacture, that will say it is not possible up to this level, but okay, let's say the company wants that I need to get data from 16 cameras. So now the company will say, no, that is not possible. Let's have only up to 10 cameras, or let's have two cameras at the front of the car and two behind of the car. Only four cameras will take, and then we'll process it. So this is the specification stage. In this stage only, what the chip will cost, everything at an overview goes on, right? Next, we go to the architecture. So this is again a very top level um, stage, here what happens is we break down the chip into smaller parts. The understanding only. Let's say it's a full adder, as simple as something. So here we'll only see, okay, it needs 2 half adders and an OR gate. Fine. We'll not go into the details of half adder and okay, it requires XOR or other things. We'll just stop at the top level architecture. Only break it into small devices. Let's say it's a complete chip. We'll just break into, okay, we need digital and analog. In digital, uh, I need some counters, I need registers. In analog, I need a PLL, phase lock loop, and okay, I need 1 or 2 ADC. Just the structure. From architecture, we go to RTL design. Okay, here this is a lower level than the architecture. Fine. Here the code is written at RTL level. We'll see it ahead. Then we'll verify that code. Okay, that if you have written it functionally, is it correct? If you have written an adder, does it actually add, or have you done some mistake in writing the code? So if verification is not correct, here a loop goes on. It'll go behind again to the RTL design and it'll come again. Okay. From this functional verification, we go into synthesis stage. Uh, so in synthesis, what happens is, up till now, our design was independent of the technology. Okay. From synthesis stage, it is becoming technology dependent. We'll talk about what is technology and what is technology dependent. So it has become more lower level and complex. Next on, we do design for testability. Okay. And I work in this design for testability team. Here, the extra circuits are added, extra hardwares are added, so that we are able to test the device properly. We are able to have more control over the 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 different elements of the device. Okay, I'll talk about this. I'll talk about this not in very much detail, otherwise I'll go into depth because this is my team. Next we go into floor planning. So floor planning, as the name suggests, similar to that, you'll just plan very properly where to keep these blocks, how to keep all the blocks with the best of the ability to have minimum area, and not just minimum area, to have least delays. Okay, timing is a very important issue. Okay, we'll see this again. From floor planning, we go into placement and clock tree synthesis. Again, after floor planning, we actually put those elements into the chip, and we also uh, add buffers and inverters in the clock paths so that timing delays are matched. We'll see this also. Then is the routing phase, where all the blocks are joined, wired. Okay, from this we go into physical verification and sign off. Okay, sign off are the last series of checks before you can confirm that okay, you can tape out this chip. From there on, the chip is taped out and fabrication and packaging is done. You see, IEC 741 comes in a package. So once you see inside that package, there is another layer, and inside that there will be a chip. Okay, this package and the pins extra added, those are done in this stage, and then you get the chip. Now we'll talk about each step in. I've talked about these, but let's see. So yeah, first is the conceptualization and specification phase. As I talked, the requirement, what will be the market value, how much resource both the companies will allocate, is it feasible or not, and they'll just describe the functionality and the architecture on a very abstract level. Okay, not into much depth. Is it done? Okay, ADC will not go into how many bits ADC, or like, even if how many bits ADC will not go into exact function that it is a one, like it works on a single pulse or it does not. Okay, but for example, for counter, see, they'll decide that okay, how many bits of the counter will have, and the reset will be synchronous or asynchronous. We'll not go into the detail that how we actually implement it. That is at a lower level. Okay. So this is very abstract level, but feasibility is the most important part. That will it be? Uh, is it something realistic? Next is the architecture, and this is the high level architecture. It is also called high level design. Here, what happens is we'll break it into the small elements like registers, ALU, instruction, and memory, right? But not inside those. We'll just keep it into blocks. Fine. After this architecture, now we actually have to get whatever we have thought. We have to get it coded. Otherwise, we can't make the chip directly. Okay, we need to get it into a programming language, and then we'll move into lower level of abstraction. We try to code it as a computer coding gets done. From there on, we try to reach up to transistor level, and ultimately, when I have that complete code initially and then the design, then I'll just print it on the wafer. Fine. So this is the architecture, high level design. Next, we go into the logic design, which is also called the HDL coding stage. So what happens is we don't code it into normal programming languages. Rather, we code it into hardware description languages. Okay, like Verilog, and in some cases or previously VHDL. Okay, and in Verilog, what happens is you have levels of abstraction. Now, what is levels of abstraction is with what precision or with what complexity are you defining the design. Let's say it is an adder. At one level, I can just say that okay, you just um, add two numbers. So I can just tell it in an algorithm manner. You'll give a, give b, and it will give the sum of this. You go into a level deeper, and then you'll have to say it in a digital sense that okay, which gates you need actually. Okay, or what can be implemented. So here we write in language form, like a and b, right? A or B at this level. And here we talk about how the data will be transferred. Okay, we use uh, symbol, we use always, and these blocks are used in at all levels. Okay, we use blocking and non-blocking statements mainly at this level. Okay, so at what clock pulse do you want to transfer the data? Okay, and is it edge sensitive or level sensitive? These. Another lower level of abstraction would be a gate level. Okay, and it is also called as structural level. Here you may define it into a very lower level, and sometimes it is also at switch level. Okay, transistor level coding, but that becomes very complex to code. Okay, so we do it usually at the RTL level because it is similar, somewhat intermediate. Algorithm way is too abstract to understand. Okay, it's just like a language. It is very close to normal language, and gate level is tough to code at the first instance itself. So we go into the RTL level coding, right? Now here what happens is different teams are given different blocks, and okay. Mm, so after this coding is done for different blocks and they are brought together, or the flow that usually takes place in the industry is all the blocks are tested individually first, and they'll be combined, and then complete testing will be done. Okay, and I'm not talking about design for testing, verification. Okay, now the next step after this designing will be verification. Who will make sure that the code that you have written is correct? If you have written a counter code, you need to see it through simulation, through waveform, somewhere that okay, yes, a counter has been uh, understood by the system. Okay, so in this step, functional verification, test benches are written for different cases. Let's say you have coded a AND gate. Okay, so how can I confirm that this AND gate is correct? By giving all the four inputs. I'll give 0 0, I need to get 0 0 1 1 0 and 1 1. So only in 1 1 case, if I get 1, I may say okay, that this AND gate is valid, it is correct. For that, you need to write a test bench. Okay, and after writing the test bench is again a Verilog code. Okay, which gives the inputs to your code, and it will test if it's working as per the specification or as per what you have given the functionality. So thus it is called functional verification. Okay, so if it is a counter, you'll give the clock from outside, reset and enable logic, and you'll see at the output. This is called also called simulation. You'll simulate the counter, and you'll see if the counter states are going like this from 0 to C, or how whichever bit counter you have done. Then sometimes you'll give reset at any stage. Let's say after 9, so you'll confirm that is it getting reset. Sometimes you'll stop the enable signal, and you'll confirm that okay, is it depending on the enable signal also. Fine. So this is functional verification, and verification, not just functional, like total verification takes a huge chunk of the chip manufacturing process. Like more than the design, we focus on verification. We don't focus, we need to, because you understand, if you need to design a simple, you need to code an OR gate, you just have to write A or B. But if you need to verify this simple OR gate, you need to have 4 different inputs. You need to test it in all the 4 conditions, right? So thus verification takes major chunk of this whole IC design process. Next is synthesis. So now till this point of time, I did not talk about what should be the channel length. Look, this is a counter. Inside that, it will be flip-flops. Inside the flip-flops, it might be realized with gates. And inside the gates, it will be MOSFETs ultimately. But we did not talk about what will be the channel length. We usually talk about technology. We say talk about channel length. Okay, it's a 40 nanometer technology, 28 nanometer technology, 14 7 5. Okay, so till now we did not talk about this, but it is decided beforehand that what will be the channel length, which technology will it be. This step, synthesis, this breaks down into code to become it technology dependent. What happens in this synthesis stage is you give the RTL to the tool, and you need to also specify the libraries that you will be using. So libraries means the technology dependent primitives. Okay, if it's an AND gate, okay, you have a complete list. Okay, 40 nanometer technology, AND gate and OR gate, all the small chunks that you need. So see, it takes place in 3 steps usually. This is the RTL designs. Okay, you have if and begin, these types of code. What happens is it realizes that okay, what does this code actually mean. Okay, if it is residue equals to state table, so I need to have maybe a buffer here. Okay, I need to assign this value to something, so it will translate it into the gates. Fine, without any timing information. It's till now we are not talking about how much delay this gate will be. Like usually it does not happen that for an AND gate you have 0 0 in the input, and at the same time you will see output as 0. There's a delay. Till now it will not talk about delay, but it's technology dependent. And the next step, what happens is it optimizes it, and it maps it to the library cell. Like okay, what is the meaning of optimization? Sometimes let's say you have 2 inverters, and it is finding it redundant that or let's say there is a buffer, and there is no need of this. You have not preserved it. You may have coded it mistakenly. So what it will do is it will delete that buffer, and it will just join it with a wire. Just see here. Okay, there are 2 gates, and it thought that it could optimize it. So it optimized it into a 3-input gate individually. Why 2 delays of 2 different gates, right? So this happens in optimization, and this is completely the designer's choice. Sometimes you have put that buffer necessarily. You want a more delay in that path. Okay. Sometimes you have put 2 inverters so as to have some delay in that path. So then you need to specify that you don't want to optimize your design. Fine. And it is mapped to the library cell exactly like AND gate. So it will see in your library that okay, there is a AND gate written 40 nanometer. Its input delay is this, output delay is this, and all the other information. So from now on, your design has become technology dependent, and it is also called gate level netlist. Okay, it is called netlist. After the synthesis, you get RTL is converted into gate level netlist. So any doubts up till now? Let's see. Okay, there are questions in this verification because the number can go extremely high. Yeah. So okay. So this was yes, you're correct. Not it is not done in this way. This was just a small example of an AND gate. Okay. Usually, what happens is it is done for a complete circuit, and we don't do it for every single gate and uh, every small flop. Rather, it is done usually uh, for different extreme conditions. Okay, that is why, because verification is, and everything there human intervention comes. Otherwise, it would have been done by a computer. So you need to understand that okay, my functional requirement is to get always 1 here. So why I need to test 0? I'll ignore it. Okay, so it is done very judiciously, but yeah, most of the conditions we need to check, and it is not done at that lower level. That was just for explanation. Uh, so we can move ahead.
Yes, sir.
Fine. Fine. So now your design has become technology dependent. Fine. After this synthesis, RTL you had written at a very higher level, A and B. Now it has actually understood that there is an AND gate which is of 40 nanometer technology. It has a delay of this, like if every node and every thing is written there, that if input is given at this time out and A and B are given at this time, after how much time output C will be reflected. Fine. After synthesis, we go into the DFT phase. Now, what happens in DFT phase? Just excuse me. Here we add some extra logic to our design so that we are able to control and observe the internal nodes, and we are able to test the chip properly. Okay. Now, what do I mean by this is, let's say you have 100 flip-flops in the design, and you have 2-3 ports in the chip. Okay, or let's say 5 ports. So not all the flip-flops will be connected at the top. Some flip-flops will be connected internally. Um, if I can draw something. Let me know when it is visible.
It's visible, sir.
Okay, fine. So see, this is your chip. and let's say it has 3 inputs and 3 outputs. Okay, now you have 4 flip-flops, or let's say 5-6 flip-flops at different places in the design, and you have some gates. This is an OR gate. Please excuse the drawing. Okay. Let's say this is connected to this directly. Here, this is an AND gate. It is getting output from here. I mean input. This is connected to this OR gate. You have another flip-flop connected to OR gate. Here you have an inverter, buffer, AND gate. It's connected to this. I think okay, buffer, and this is get into. Okay, fine. So these are the flip-flops. Okay, other are the gates. So if this is your chip and you want, so sometimes what happens are there are some manufacturing defects. Okay, what do you mean by manufacturing defect is while layering this wire, okay, while layering this wire maybe it got connected to a VDD wire. Fine. A wire which was VDD, maybe going through this. That wire was also printed on the board, and this got connected to this. This node is said to be now stuck at 1. Fine. SA1. Because it will always be 1, irrespective of what output is from this flip-flop, because it has got stuck to VDD. Similar condition may happen that this wire, there was a ground pin going through this, and this wire got connected to ground. So this point will always be stuck at 0. Okay. Irrespective of what output you get from this flip-flop. Even if it is 1, this wire will bring it to 0 always. And you will have 1 at the output all the time. These are the some kind of manufacturing defects that we get. Stuck at defect, these are called. And these are obviously not intended and they need to be avoided. Fine. For this, we add some circuits, and that is done at the DFT level by DFT engineers. What do they do is, okay, so if there is a stuck at no point at here, how will I judge it from these 2 pins? Because at the outside, I don't see the circuit entirely. I only have access to this point and this point. Okay, only the inputs, all the inputs and all the outputs. I don't have access to an internal node. I'll only notice this difference when something at this will be error out, and I was expecting 1 here and I was expecting 0 here, and it's always showing 1, but I don't know which node is faulty. To test this faulty, which node actually is faulty, we do DFT. Now, how do we determine is, I'll show you. Okay, I'll show with the example of only, let's say, 3 flip-flops. One was somewhere else, and this. So maybe, okay. So what we do is we add a mux in front of each flip-flop. Earlier, this was not the case. Now we have added this mux in front of all the 3 flip-flops. Now it has become it is called a muxed flip-flop. So its inputs are D, clock, and Q. Again here, D clock and Q. Clock and Q. So this mux will be connected to this, all the three. So we can't break the functional path. Functional has to be there. So mux has two inputs. This will come as natural. Maybe this was coming from an AND gate. It will come as naturally. Okay, we will not play with that. We can't. Okay, functional has to be correct. Okay, so let's say this was the functional setup. These two were coming from some other generator block, anything. Okay, so this was working as it is. Now what happens is, so I have another input at this mux. This I have control over. Okay, so it is connected like this. I used different color, but okay. And see this mux, other mux select line also we have control over. All the select lines will join it. Fine. Yeah. So okay, this may have become confusing, but let's see. So this mux we can operate at two different levels. This line, the select line of this mux. Okay, this is called scan enable. If I put scan enable as 0, this D will be selected, right? Here also this normal D operation will be selected. Here also D will be selected. So scan enable this signal, the select line of the mux, if I put as 0, then my chip behaves as it is in the functional stage. So this mux did not put any problem. Does anyone has doubt up till now?
No, sir.
Okay, fine. Now the second configuration will be, so this first need is satisfied that I should not, I added a mux at every input, at every flip-flop, but I cannot play with the functionality of the design. So if scan enable is 0, this mux is as good as a transparent element. So my device will work as it will in the functional mode, right? Second will be when I put scan enable as 1. Now the device has entered the test mode. Let's see how. So see, if scan enable is 1, this input of the mux will get connected and this will be disconnected. Okay. Similarly for this path is broken. I'll erase it so as to make it easy. And same will be case for this. Okay. The functional D path will not be selected now. Fine. And these are scan enable, you know it, that these three I have put as 1. So I'll erase this also, because maybe the next step will require a bit of clear drawing. Okay, so you're understanding, right? Everywhere it is 1. This can enable 1, 1, and 1. Now, if it is 1, what happens? My circuit gets this, goes to D. The output of this Q goes to this D. This output of the Q goes to this D, and this is out. So are you able to see it is somewhat like a shift register? Input this and output this.
Yes,
Now, yeah, now finding error will be very easy. Let's see how. If I have a doubt that, now we'll do testing for all the condition. Let's say if I have a doubt that this wire may be coming from some other input, was stuck at VDD at 1. Okay. So what do we do is we do a simple chain test. We'll send 1 1 1 at the input, right? So we'll send this first one. It will go at D. It will stay at D, and on the first clock it comes at Q. At Q, but okay, this is a common path, so it sits at D. At the same time, second input will come. It will be at D. At the second clock, this goes here, and this first one comes to this flop, and the third one goes inside. And after 3 clock pulses, I can get these out as 1 1 1. I'll get it reverse. Okay, if it is 1 1 0, this first one goes inside first and comes outside first, so it will be 1 1 0. Okay, but I matched it. Okay, input is equal to output. Fine, there's no issue. Sometimes if there will be issue, the values that will send, and thus we send different values, you'll not get the exact same value out of the output. Okay, so this is one of the techniques used in DFT so as to counter the manufacturing defects. Okay, we make now these are called the patterns. This simple 110 which you sent, this is called a pattern. So this pattern will be run on the chip so as to test that this path is fault free. And there are many techniques used. This was one of them, a major technique. Now let's go to the slide. Yeah. So this was the thing, scan flip-flop. Now it was all about controlling and observing, controlling a node and observing it. The other techniques used in DFT are memory based. ATPG is automatic test pattern generation. We generate patterns. There are memory testing and there are logic testing separately. Now how again it is beneficial, you can understand these days logic bits are used, and what happens is when you start your car, okay, if there is a logic bit, we don't need logic bit everywhere, we need it only at the important points. Let's say engine. So let's say if your car starts, before it will begin completely, what happens it runs a logic test very fast, and it will see if it is in the brake there is some fault. Okay, then either the car may not stop, or you will, or maybe if a backup has been set for that will work. Okay, but it runs on the fly. Logic based and memory based, they run while you are operating at the machine also. Okay, so this is DFT. Next step, we move on to floor planning. Floor planning is similar to how you plan. Let's say you shifted to a new house and you have all the stuff from your house, your bed, sofa, and fridge, and everything. So floor planning is exactly the same. How you will plan to keep the things at proper places. You won't keep everything at once, and you will see that how you can utilize the area to the best of the abilities. Same is the approach in floor planning of a chip. We try to minimize the delay. And how do we minimize the delay? By keeping the blocks closer. Okay, and we try to keep it as in a as low area as possible. Now there are two different kinds of blocks. Okay, some are hard blocks, some are soft blocks. So hard blocks area is same, but you can vary its aspect ratio. Like you see the example of A and B. Block C is a soft block. It has been kept horizontally, and other time it has been kept as vertically. So we'll obviously choose the first one. Okay, so this we also need to consider, that how you put the hard blocks, how you put the soft blocks is just the overall planning of the chip. Fine. Next, I may have or I had told that now one of the most important steps is timing analysis. Okay, and this happens at almost every stage. timing analysis every time, before routing, after DFT, after synthesis, before DFT, after CTS, before CTS. At almost every stage, we need to have timing, because that is the most important part. How fast my chip will work. Speed, area, power. These are the three most important things. So how fast my chip will work and how low the area it will take. So yeah, so let's talk about timing analysis, which is, so you would have heard about STA and not, if not, then okay, let's see. What happens is, in STA we check for the timing violations in all the possible paths. Okay, like if you have intended a data to reach from point A to point B in 3 nanosecond, does it actually reach? Okay, does it get captured by the flip-flop at the time that is required? Does the flip-flop have a delay that can be respected? Okay, now in timing analysis there are 4 paths. I'll not go much into detail, but see, this is a simple design, and you can see 4 paths. Okay, one is path 1, that is from input to a register. At D terminal you have to stop. Okay, so this is path 1. I'll talk about path 2 later. Let's see path 4. That is from A to Z there is a wire. So that is called an in to out path. These all 4 paths are treated differently. Okay, fine. The next is path number 3. That you see is from a register to an output. That is called reg to out path. Fine. Next is a reg to reg path. Path number 2. Okay. These are the 4 different, and based on this we do different kind of analysis. Now the 2 timing checks that we do are called setup time and hold time. These are very important. What is setup time is, it is the minimum amount of time required for the input of a flip-flop to be stable, okay, before the clock edge. Let's say this is the clock edge, okay. So their requirement is, there has to be a certain time, a minimum time before this, that the data should stop changing. If it changes within this time frame, the data gets corrupt. A simple analogy would be, you need to reach, when you have a flight, you need to reach the airport at least 2 to 3 hours before. That is the setup time. Okay, you need to be there stable before some time. This is called the setup time. Hold time is the minimum amount of time required after the clock edge. Even after it gets captured, to be sampled properly, it needs to be stable for a certain amount of time. Okay. Yeah, so these are 2 very important points, and this is a simple diagram which shows, this is a clock, okay, and this is the setup edge and this is the hold edge. So after this hold edge, data must be stable for a certain amount of time, and before this setup edge, data must be stable. If it is not, data gets corrupt, and again a complete analysis for this is done, that every flop should respect the setup time. If it does not, then how do we change it? If data gets changed at this point of time, you have two solutions. Shift this clock ahead, okay, or pull this data back. Now pulling data back is tough, because you need to remove some element maybe. So you need to add some delay in the clock path so that this edge gets shifted ahead. Fine. So after timing analysis, there is one step which is called clock tree synthesis. Okay. So what this step is, it makes sure that clock gets distributed evenly throughout the design. And thus we try to keep the clock blocks like PLL in the center during floor planning, so that it reaches every block at a specified amount of time with lowest delay. Now this delay is for clock has some particular terms which is called skew and latency. These are the definitions. Now I want if someone can say which one is skew. Okay, this is difference in arrival of clock at two different pins at a sequential element. Second is the delay difference from the clock generation point to the clock endpoint. So this I name 1. And this I say 2. So can anyone say which one is skew and which one is latency?
Sir, second is skew and first is latency.
Yes, correct. Okay, and those, if we are not clear about this, yeah, please see it. And we usually see for the skew timing for setup and hold. Okay, we see that the skew is positive. The clock should reach the second element later. Okay, we see the skew is positive. So if you have two flip-flops back to back, from the start point, you'll measure the time taken by the clock to reach CP pin of the second flop minus from the start the time taken to reach the CP pin of the first flop. That is called skew. Okay, latency. Yeah. Similarly, like if you start from a point, okay, and if you consider this as a tree from a clock, a clock is generated from a generator which is called PLL, phase lock loop. From there on, it reaches all the sequential element. That delay is called latency. So we want latency to be evenly distributed. You can't remove it, but we want it to be evenly distributed. Okay. Yeah. Next is, okay, we add buffer and inverter in the path to counter the latency and skew. As I told, setup and hold fixing by pulling and pushing the launch or capture clock. And we want these latency and skew to be as low as possible because these are undesired delays. Next step is placement and routing. So it could have been talked along with floor planning. So once you floor plan, you put all the elements in the space that you have allotted it to, and then in the routing they are actually connected through wires. These are not as simple as I have explained or as simple as they may seem. There are so many considerations that we need to take regarding where a memory element should be put, where the hard blocks should be put, where the soft macros are put, where the blocks from the third parties are put, like some blocks a company buys from some other block. So where do we put it? Where the clocking generator points should be put. If a block has too many inputs and few outputs, so it should be shifted towards inputs so that the output wires can be stretched. But maybe it has very many inputs, so put it closer to the inputs. Okay, so there are many considerations taken place in the place and route and floor planning stage. And after this, we have this tape out and sign off. Sign off are the complete checks, okay, final verification that we do. And you confirm that, okay, now this chip can be taped out. Fine. And tape out is the result, like the final output that the design groups send is a GDS format, GDS2 format. Okay, so that is taken ahead and then it is sent in the fabrication for manufacturing. Okay, so these are the back-end processes. Fine. I had just added this for some extra information. This is a chart which you might encounter in your subject. And this helps us to understand the different levels of abstraction. This will be a common thing to talk about, the levels of abstraction. So see, there are three different domains that this talks about. This is the Y chart or the Gajaski cone chart. It talks about three different levels of hierarchy. It's behavioral, structural, or physical. Okay, this is apart from this ASIC design flow, but everything is linked. You may you may relate things. Okay, that's why I thought just to add this. Now, behavioral level, as you understand, we are talking about behavior. Now, what behavior? You talk maybe about systems. That my system is taking temperatures as input and giving me voltage as output. As abstract as this. You may talk about algorithm, simple as adding, subtracting. Okay, you may talk about RTL level, you may talk about logic. So these are very abstract level, behavioral, very top level. Next, you may go a bit inside it and you talk about the structure. You may break the system into smaller parts. You may break it into ALUs, RAMs, gates, and flip-flops. Okay. And then if we go lower, then you can say the gates are made into transistors. Okay. As you go inside the circle, see, then you get into a lower level: processors, ALU, gates, and transistors. Similarly here, system top level, then you go into algorithm, RTL level, logic, and transfer functions. Now the physical level is the final level which goes close to manufacturing. You start from systems, you go here, and then you go into structural, and then you go into the physical level, and then transistor layout is the final point. Now, first you do the physical partitions, that which block you'll need, you do the floor plan, you lay out, okay, placement and layout process. And finally, the cells are also broken down into transistors, and that is printed. It is patterned on your device, right? And then you get the final chip. So these are some sources that I took. And yeah, I think I'm done. And if there are some questions, then let's take them.
Sir, what do you think is the future of hardware industry, sir? Like,
As in what terms?
as in terms
Like,
of opportunities, growth,
okay.
and
So, look, even I have had only 2 years in this industry. Okay, graduated in 2019. But with whatever I have seen and whatever analysis that is going on there, there is a very close intermixing that I can see with the softwares. Okay, even now it is inevitable. Okay, because the tools are getting very sophisticated. But that is a long term I'm talking about. Immediate impact is not many. Uh, yeah, there are like AI and ML is getting into this, and there are again twofolds effects of these. Since it may make the chips more complex, so you need more skilled people. Like you need to, at the current level, I say that there needs to be a balance about software and hardware in your skill set. If that is the consideration. And chips, in general, chips are getting complex. Obviously, we are going into a lower technology node. We have gone, I'm not sure, like 5 nanometer. Till that I had the information. Okay, 7 already devices have been produced by Samsung. I suppose TSMC has gone till 5. Now, what beyond that? Either a new technology node, new complete new technology might come. That is again cannot be said for. Just as no one could predict that BGT will be completely replaced by MOSFETs, or either we may, obviously there are FinFETs and other devices coming on, but yeah, technology node is something that that we need to see. What
Thank you, sir.
beyond that?
Thank you so much, sir.
Yeah. And regarding opportunity wise, if you're saying, there are no, I don't think there are many immediate effects. Even like some of the top people have said that they were less of the resources crunch now and more, and they had so many more chips to produce. So yeah, that this is an like it's a welcoming field for now, as per I think. Not just Indian perspective, or I'm not talking about fresher perspective, or like you will get something or this way, but in general, it is not going through a lower phase.
Thank you, sir.
Yeah, welcome.
As you said, the design tools are getting way more advanced. So in
Yeah.
the future, do you think like for design, obviously people will be needed to create those designs, but for things like synthesis and layout, or do you think that human involvement will become like absolutely negligible and everything will be done by the software itself, or will there still be a
No.
need?
There are works going on. Okay. See, this is a paradox that people are inventing things that will reduce their own work. So there are work going on with some tools which will begin at the basic level, and it is a like I'm not sure if it is already out or if some works are going on, but I had heard it that it will begin from, I think, the specification or RTL stage, and it will take it through all the considerations. Like initially you need to give and specify all the inputs, and it will take you throughout the process, a single tool. Now whichever steps that I talked about, almost every step requires a different tool. And there are uh, look, there are two different kinds of companies. Okay, one is the EDA company, and second are the design house that we say. Okay, EDA companies are, the top EDA companies are Cadence, Mentor, and Synopsys. What they do is they provide the tool to run these. Other companies like mine or others, okay, like ST, Intel, Qualcomm, these are design companies. They take the tool from these EDA companies and then they run it. So let's say for verification, we use a tool from Cadence, which is called Xcelium. Okay, for ATPG pattern generation, we use a tool Tetramax from Synopsys. For DFT MBIST, we may use tool from Mentor Graphics, Tessent. Similarly, for synthesis, we use Design Compiler. So yeah, human intervention is already getting lower, but since it is getting very complex, so the tool also is in a process so as to compensate. Not everything at every stage has become fully automated. Even at the steps which were considered automated, that is not the case. But yeah, in very long term, uh, it might be the case, but not completely replaced, because it is not a very fixed process. Okay, you obviously tool needs to judge certain things, but there are many redundant elements which the tool is not able to judge. Let's say you have a very small example is, let's say you have a port open. There are two different considerations. It depends on you. Okay, so here human intervention will come, that you want that port to be at it throughout the end, because you have decided something that that I will connect that port to VDD at the end. Or you will want, you say the tool to optimize the design, then what happens, it will delete that port. Okay, but the control should be and has to be with the people, because you cannot rely on that. So yeah, maybe the number will decrease, the number of people, but it will require more expertise. Let's say there are only 2-3 people required, maybe in a team which took 10, but the expertise required, that will be even more, because now the tool is processing at a higher level than it was accustomed to. Now you have to look at 3 stages after once. Maybe it has done RTL design and verification, and then after verification you have an output that you need to analyze. So you'll need more expertise, or maybe the complete setup may change, that you won't need certain engineers, but certain profiles which have not been even developed yet, that will be needed. Because a few years back, maybe uh, logic based and memory based was there, but logic based was not that much relevant. Even now it is not done in every company. So but when it came, and then the need was, it was not as such a need, but it solved so much purpose, and then a complete new field has come. Logic based different testing has done. It helps you test on the fly, like you can understand. Otherwise the testing are done on ATE, automatic test equipment, but this helps you test on the fly. You're like driving, and back in the background memory testing is going on, and all the memories, like memory, maybe if it is not that important, it will test and it will report you later. Otherwise, if it is an engine, it will test in the beginning, it will not start your car. Getting dead in the between, it was far better to like not even get your car started. So yeah, new things are coming. The Obviously, when you were studying or when I was studying, we did not know that this is a field in which we'll work. So uh, now at least you're in college or you're closer, you'll know the people who are studying in school, maybe now they have started coding, but they'll work on technologies which has not been even invented. Most of the people, whatever they study in the beginning, they don't even work in the technology that they actually work. Would have not even seen it. Okay, so that similarly is the case here. This might get into this, but it can't be redundant. Yeah.
Thank you, sir.
Is there any significant design changes from FPGA to ASIC? See, FPGA and ASIC is specific. It has been fixed. Now it will serve only this purpose. And if you'll see FPGA boards in your labs also, you'll work. So that is the name, field programmable. So that is programmable on the field. That can be programmed on the fly. You can do different. You can configure it for different purposes. Yeah, a basic structure and a basic working is fixed, but you can use it for different applications. ASIC is not that. ASIC is already designed for a particular application. CDC, clock domain crossing you're talking about. Okay, so yeah, clock domain crossing, there are many things that you can go through. First, you need to understand clock domain, and then synchronizers, and then like I am not into that field and I don't know the research that is going on in clock domain crossing. But yeah, that is again a very important and a challenging topic. Mean time, MFTB, those things you can see. Okay, mean time before failure. Now how the 2-step synchronizers and 3-step synchronizers work, those things you can see. But yeah, the current day research I'm not well aware into about clock domain crossing. I'm not seeing that, and I'm not even actually working in that team. So yeah. Is there any, what companies expect from fresher? Any specific profile? As such, no specific profile in demand. No, and you should, as a fresher, you cannot be targeting a specific profile. As a fresher, it is expected a very general information, like you need to have a breadth of knowledge. Okay, it does not require how much deep you obviously look. The kind of knowledge that is preferred throughout, that is called a T-shaped knowledge, right? You should have breadth over many fields and you should be expert in one. Now that cannot be said for a fresher, so you need to know multiple things because you have studied the subjects also. So some subjects which are important, I had made a complete document in this. I had shared also. Maybe I'll share with someone I know, Biral. Okay, I'll share with him. He can share with all of you. So there I had compiled the list. Okay, and what? So from freshers, what exactly is everything? Everything and a basic understanding like digital microprocessor, VLSI, Verilog coding, FPGA. But it's not that so much into FPGA or so much into one field. Okay, digital you need to be good at. Verilog you need to be able to code, and almost similar on similar lines you'll work unless you are in an analog team. Or yeah, even verification you need to understand Verilog, you need to have knowledge about digital. So yeah, only all the, like, you need to be good and not expert in almost everything. STA you can see from there's a site vlsiexpert.com. That is far more than enough for STA. You need to just understand what is setup time and what is hold time, and some definitions if you want, of like what is a false path, what is multi-cycle path, those things. But yeah, if you are able to explain setup and hold properly, that's enough. Yeah.
Okay. Yeah. I sincerely thanks, sir, for spending your valuable time to provide a clear idea about ASIC design flow to all the participants in the event. And a big thanks to all the participants for attending the event in big number and making the event successful. I think we ECA hope you all gain some knowledge about ASIC design flow from the event. Thank you all.
Okay. Thank you everyone. Thank you for your involvement. Okay, so thank you, Aditya and ECE Association. I think now I'll disconnect then.
Yes, sir. Yes, sir.
Okay.
You can end this.
Okay.
Yes.
Thank you. Thank you, everyone. Bye bye.
Thank you, sir. Bye.
Thank you, sir. Bye.